In this section, we're going to look at prime numbers and factorization. And the first thing we want to do is look at different divisibility tests. Now, these are very easy to perform, and they don't tell you how many times a number goes into another number, but it is very important that we understand these, because this is right at the heart of all the things that we're going to be doing with fractions. First off, if we want to determine if a number is even, basically we want to know if it ends in 0, 2, 4, 6, or 8. You might say, is this number even? If a number is even, then 2 divides into it. A number is divisible by 5 if it ends in a 0 or a 5. A number is divisible by 10 if it ends in a 0. Now, the test for divisibility by 3 is a little bit more involved. We ask, is the sum of the digits divisible by 3? For example, let's take a rather large number, such as 456,702. We want to ask, is this number first divisible by 2? The answer is yes. It ends in 2, an even number. That means 2 goes into this rather large number. It doesn't tell us how many times, but it does tell us 2 will go in. Does 5 go into this number? No. It doesn't end in a 0 or a 5. Does 10 go into this number? No. It does not end in a 0. Does 3 go into the number? Well, we're going to look at the digits and go 4 plus 5 plus 6 plus 7 plus 0 plus 2. Well, that adds up to 9 plus 6 is 15, plus 7 is 22, plus 2 is 24. That is the sum of the digits. And then we ask, does 3 go into 24? Yes, 3 goes into 24 8 times. Therefore, this number is divisible by 3. Now, if you want to ask whether a number is divisible by 6, since 2 times 3 is equal to 6, if a number is divisible by both 2 and 3, then it is also divisible by 6. This one was divisible by 2 and by 3. That means 6 goes into this large number. It doesn't tell us how many times, but 6 will go into this large number. The test for divisibility by 9 asks, is the sum of the digits divisible by 9? So it's just like the test for divisibility by 3. In this case, the sum of the digits is 24. 9 does not go into 24 evenly, so 9 does not go into this large number. Had the sum of these digits been 27, such as changing this number to 3,456,000, then we'd have 3 plus 4 at the beginning there. This would add up to 27. Now, since 9 goes into 27, 9 would go into this newly changed number. A number is prime if the only factors it has are 1 and itself. For example, the first prime number is 2. The only multiplication problem that makes 2 is 1 times 2, 1 and the number itself. 3 is a prime number because 1 times 3 is the only multiplication problem that makes 3. 1 and 3 are the only factors. 4 is not prime because if you take a look at 4, it's not just 1 times 4, 2 is also a factor. 2 goes into 4 2 times. 5 is a prime number, 7 is a prime number, 9 is not a prime number because 3 goes into 9. The only even prime number is 2. All other even numbers have 2 as a factor, so at this point we only look for odd numbers. We're skipping 9, we go on to 11, 13, 15 we skip because 3 and 5 are factors, 17, 19, and so on. I've only listed the factors here that are beneath 20. Now, we'd like to say that if a number isn't prime, it's composite, and that is the case for the most part. But 0 and 1 are neither prime nor composite. Now, in the case of 1, the only factors of 1 is 1, not 1 and the number itself. It just, by definition, we say it's neither prime nor composite. 0, the same thing. Every other number that doesn't fall into one of these two categories of 0, 1, or these prime numbers is then composite. So the 4, the 6, the 8, the 10, all these numbers that we skipped over here, including 9, those would all be composite numbers. The next set of directions I want to look at is that of finding the prime factorization of a number. Let's take a number such as 20. Now there are two different methods for finding the prime factorization. One is the factor tree. You find a multiplication problem that makes 20, such as 4 times 5. And you break these down by multiplication. Here I would have 2 times 2, and the only multiplication problem for 5 is 1 times 5 because 5 is a prime number. So I'm going to just bring that 5 down, and none of these numbers will break down any further without involving 1. So the prime factorization here would either be 2 times 2 times 5 written in expanded form, or 2 squared times 5, which is the way we usually write this. We always put our prime factors in numerical order and include the exponents as appropriate. Now another way to do this is to take the number 20 and start dividing out prime numbers. For example, 20 is an even number, and we can divide by 2 and have 10. 10 can also be divided by 2, and we can get 5. And we look for prime numbers that will go into 5, such as 5, and all we have left is 1 here. All we have are prime numbers on the side, and you can probably see it here. 2 times 2 times 5, the numbers on the left are our prime factorization. Now, the one thing you've got to be careful of when you're making these factor trees is that you don't leave a number up in a tree if you're doing a lot of work. Always bring numbers down to the next rows. You also have to be careful that you don't take a number like 20 and split it up into 10 and 10. It's not 10 plus 10, it's 10 times 10 would be 100. We're always looking for multiplication problems, not splitting things up in addition. Now let's find the prime factorization of a number like 96. I know the number is a little bit large, and that's not a multiplication problem we're used to, but we do know it's even. We do know that we can divide by 2 and have 2 times, well, we have to think about it, get 48. At which point 48 is a little bit more comfortable. We know that that breaks into 6 times 8. I'm going to bring my 2 down. And then my 6 will break into 2 times 3. I'm going to continue to break my 2 down. Now, with my 8, normally we go 2 times 4 and then break the 4 down. I see 8s so often, I just get used to making that 2 times 2 times 2. Now, all of these numbers in the bottom row are prime, and all we have are 2s and 3s. So I'm going to write 2 times 3. The 2 shows up 5 times, and that would be 2 to the 5th times 3. We could also use the other method of dividing out prime factors, as I showed you on the last example. Let's do one more of these problems, and I wanted to use a large number here to emphasize how important it is to know your divisibility tests. If you have 840, notice how it ends in a 0. Instantly, we can write this as 10 times 84. And then we can break these each down into prime factors. 10 breaks into 2 times 5. 84, again, a rather large number, so let's be on the safe side. Let's go with 2 times 42. 42, okay, that breaks into 6 times 7, and you really do need to know your multiplication tables here. I'm continuing to bring down these numbers. 7 is a prime number, so that all we have left to break down is 2 times 3 there. So I will bring these remaining numbers down, and we're going to list 2, 3, 5, and 7 in numerical order. 2 times 3 times 5 times 7. The only number that's repeated is 2, and it shows up 3 times. So we will write that as 2 to the 3rd times 3 times 5 times 7 as the prime factorization of 840. Another thing you may be asked is to list the factors of a particular number. Let's take a number such as 36. Now, basically, when we're listing the factors, we're finding all the numbers that go into 36 evenly. Remember how factor times factor makes product. Factors are numbers that multiply together to make a product. Now with this 36, there's a couple ways of doing it. Personally, what I like to do is I like to list factor pairs. I like to start with 36 up here on the table, and I say 1 times something makes 36. That something is 36. Then I move on to 2. How many times does 2 go into 36? Answer, 18 times. I move on to 3. Notice how my first number is getting larger, my second number is getting smaller. It turns out 3 goes into 36 12 times. I then move on to 4. 4 times 9 is equal to 36. I would then determine whether 5 goes in, but 5 doesn't go into 36 because it ends in a 6. I move on to 6, and 6 times 6 makes 36. Now, done this way, notice I kind of reached a turnaround point. That tells me I've found all of the factors. I don't have to search anymore because there can't be any other factors of 36. Now that is listing of factor pairs here. If we wanted to list the factors, we would say 1, 2, 3, 4, 6, going down that first column. I don't need to write 6 again, so I'd have 9, 12, 18, and 36 after that. Now some people don't write it out this way. They just like to start with 1 and they write 36 off to the right, hoping they've left enough space in the middle. Then they start with 2 and they pair them up this way and generate their list. But you need to know your divisibility tests in order to generate this list, and the better you know your times tables, the better you're going to be at this.